So I will begin with a word of prayer, I suppose. Dear Father, we thank you for this time we have. Just help us to learn a little bit more about abstract algebra, Lord. And I pray. Amen. So I had some brief comments about three things, and then I'll take your questions. So the first was I want to just talk for just a minute about the definition of external direct product. I mean, we've talked about external direct product. I'm trying to find the internal direct product of three things, and I'm too close to my notes. I can't find it. I'll find it eventually, though. What's the music? Do you guys know? Here it is. So I wanted to warn you about this definition. I don't know if it's even going to be an issue for us this semester necessarily, but who knows, maybe somewhere, bonus question or something, I don't know. But if we have n groups that are all normal subgroups of a group, then we can talk about the group being the internal direct product of n subgroups, just like we talked about the group being the internal direct product of two subgroups. And the definition is pretty much the same. It's that the group is obtained as the product of the subgroups, right? Meaning that we take elements from each subgroup and multiply them together. And looking at all such products of n things, we get the whole group, right? That's one thing. But we also need this other condition, which is a little bit surprising. Because in the case of two subgroups, we just have that their intersection is the identity, right? So as you generalize that, you might be tempted to say that the condition would be that we have just intersection of like pairs, like 1 intersect 2 is the identity, 1 intersect 3 is the identity, 1 intersect 4 is the identity, then 2 and 3 intersected the identity, just pairwise intersection of the identity. That does not work. That will not suffice to give the kind of independence that we need. We actually have to insist that the product of everything except for the what? Oh, okay. Well, this is a sneaky way of saying that if we take any I of them and intersect with the next one, we get identity. This is a way of imposing the independence of the subgroups. I'm used to writing this a slightly different way, but whatever. Anyway, in this context, we have that G is the internal direct... oh, thank you. Oh, that's fine. Right here. It's all good. I got you. We have that G is the internal direct product of these subgroups. Now, just like with 2, the idea is that means that the group is isomorphic to the external direct product of the subgroups. And that's what we prove. I have the lemma. The lemma is that if we have the product of things from each of the h's equal to another product of things from each of the h's, then we get that we have equality of each of the matching group components, like A1 and X1 are both from H1. That means that A1 is equal to X1, A2 is equal to X2, AN is equal to XN. Just like we did with A and B in class. I spent a long time proving that. The lemma. So the lemma still generalizes to n things, and we also have that any, you can commute. If you take a product of n things, one from each such group, then you can reorder them any different which way you like, and you still have the same product. They commute with each other. That's just a fancy way of writing out. And the proof is here. I'm too tired to tell it to you. I'm so sorry. And then here's the isomorphism. The isomorphism from the direct product to G is given by just producting, you know, like erasing the commas and making them into multiplies, just like with A and B. You remember this, Emily. You said phi of xy is xy. This is the n-fold extension of that. It's just x1, x2, xn. And essentially by the same argument, you can prove it's a homomorphism, and you can prove it's surjective, and you can prove, in fact, it's a bijective homomorphism, and we have that isomorphism. So that's the internal direct product of 3 or more things. It works pretty much the same. It's just the arguments to support it are a little bit more tedious to establish. Yep.
Is are an and xn's, but in the second line of that kind of series of thoughts or series of statements, are an and xn supposed to be in the same
Right.
set of parentheses?
Is there a typo? Oh, yeah, that's a typo.
Okay.
Yeah, thank you. You are correct, sir. So there was that, and I also have, also if we have an n tuple, you want to look at the order of the m tuple. It's still true. It's the least common multiple of the order of the components building the n tuple. Yeah, that's still true. And here, I'm a glutton for punishment. I actually calculate the elements of order 6 in Z6 cross C3 cross C4. Why did I ever want to do such a thing? I don't know, but do you want me to, would you like to look through that? I mean, we could look through that if it'd be helpful to you guys. I don't know. Okay. So in order to have an element of order 6 here, we need the least common multiple of the order of A, the order of B, and the order of C to be 6. So how can you get that? You could get it, well, the question is, what are possible orders for A? What are possible orders for B? What are possible orders for C? That depends on their context. A is from Z6. That means A could have orders 1, 2, 3, or 6, because those are divisors of 6. B could have orders 1 or 3. Those are the only divisors of 3. 4, C could have orders 1, 2, or 4. Them's your choices, right? Now, 4 is definitely not something we want, because that won't give a least common multiple of 6, right? But we certainly could have A have order 6, and then if A has order 6, then we could have B have order 1 or 3. We could have C have order what? 1 or 2. So how many different choices are there? For B, having orders 1 or 2, we have how many choices? We have 2. For C having order 1 or 2, we have 2 choices. 2 times 2, that gives us 4 choices. For B and C having orders that would pair with A having order 6. How many choices are there for A having order 6? How many? So phi of 6 is what? Phi of 2 times phi of 3, right? So it's 2. Or you could just, I mean, that's really, do you really need to use the theory when you have 6? Maybe not. So anyway, my point here is that working through this, we have 2 times 3 times 2. Why did I get that 3 from? Oh, because I forgot I could have order 1. Everything in Z3 either has order 1 or 3, isn't that right? So I chose, I mean, there's actually 3 things here. I said there were 2. That's bogus. Because you could do 0, 1, or 2 paired with an element of order 6. And here you could do either 0 or 2. So that's why we have 2 times 3 times, the 3 is from Z3. So 2 times 3, that's going to be 12 choices, assuming that the first one has order 6. If the first one has order 3, then to get at least common multiple, I need the middle one to have order 1. I can't have order 2 in the middle, right? So order 1's my only choice. But I can have order 2 in C. So that's another possibility. That gives me 2 more elements of order 6. And then finally I can have a 1, a 3, and a 2, and that gives me 2 more elements. So in total, 12 plus 2 is 14. Looks like I got 16 elements of order 6 in Z6 cross C3 cross 14. I say it follows there are 8 cyclic subgroups of order 6. Oh, thank you. How do I know I can form cyclic subgroups? It's relatively simple, right? I mean, I take these elements of order 6, right? I pick one of them, right? And then I generate a subgroup from that one, right? In the process of doing that, how many other elements of order 6 have I covered? How many generators are there in a cyclic subgroup of order 6? There are 2. So each subgroup uses up 2 generators of order 6. So that means if there are 16 elements of order 6, then there are 8 cyclic subgroups of order 6. Because each one of those takes up 2 generators. The combinatorics here, you guys probably could find a better way to organize your thinking than I have here. It's just a way, it's not the only way. But you got to be careful with least common multiple, right? Because it's easy to forget that 6 is 2 times 3 and not just 6 times 1. Or it's also the least common multiple of like 2, 2, and 3 is 6, right? Not just 1, 2, and 3. I don't know. There's stuff like that. I make these mistakes personally. So let's see here. That's pretty much all I had to tell you guys in terms of just, lecture I didn't get to. Do you guys have questions about the homework? Or I actually brought my, yeah, go for it.
I have kind of a general question.
Okay.
Just about cosets in general.
Uh-huh.
The factors.
Cosets and factor groups. Now, can I put this away? Doesn't matter? Okay. I'll probably regret that.
Just like maybe an example that's not.
An example that's not in the notes. And then what did you, what's the nature of this example I'm supposed to create here on the fly?
Or just the method behind making them, I guess.
Well, again, just remind me your question. My memory is very worthless at the moment. So what would you say? You want an example of?
Not factor groups.
You'd like to see an example of factor groups that we haven't worked yet. Is that right?
Yeah.
That studies what issues about factor groups? How to calculate in them, or okay. So you'd like to see you'd like to be reminded how to find the basis in the quotient vector space. Yes? Okay, all right. So we had a theorem in linear algebra. And our theorem in linear algebra stated this. If W is a subspace of vector space V, that notation meant subspace of vector space, yeah? Let's say over the reals for the sake of discussion. All right, if you have a subspace W of a vector space V, not even close, not even slightly close, then if you have beta sub W is basis for W. What's that mean? Basis. What's a basis? What is a basis?
A linearly independent set of vectors that can create W.
Yes, it's a linearly independent spanning set for W, right? And beta is beta W unioned with, let's say, the k plus 1 Vn is basis for V, right? So here I'm supposing the dimension of V is n. I'm supposing the dimension of W is k for the sake of discussion. What we proved is that a basis for the quotient vector space, right? Remember what the quotient vector space was? V mod W. What was that? It was x plus W, such that x is in V, right? So this is the quotient vector space. You should recognize that if you divorce yourself from the scalar multiplication stuff, it's in complete agreement with what we're currently doing. It is nothing more than the coset space. It's the factor group with respect to the additive group structure that is implicit within any vector space. And so, what I'm telling you is relevant. Now, the basis for VW we learned was, in fact, given to us by nothing more than V, let's say Vj plus W, such that j equals to k plus 1, k plus 2, Vn. See, because essentially, if z is in beta W, right, then z plus W is just equal to W again, right? So in the quotient vector space, anything in the quotiented subspace is 0. So the basis of W, the part of the basis for V which was forming W, is of no use whatsoever. It's 0. It's the 0 vector, right? Not a good choice for your basis in the quotient vector space, right? But good news, the rest of the basis give you representatives which, when added to W, give you cosets which are linearly independent and span the quotient vector space. This is the theorem. So you can always take a basis for the vector space, and if you form the basis by extending the basis for a subspace to the whole space, whatever's not covering the subspace implies the basis for the quotient. Of course, you could also just work this out for a specific example, right? If we're working with, let's work on a 2 by 2 example, all right? So our 2 by 2, I think I gave you guys 3 by 3, right? So it's completely different. So if we're working with V equals R 2 by 2, and let's suppose we're going to let W, and I'll do something different, a little bit different. Let's suppose W is the trace, kernel of the trace. Kernel of the trace. In other words, we're looking at A in 2 by 2 matrices such that what? The trace of A is 0. All right, well, in that case, we're looking at matrices of the form A, B, C minus A, such that A, B, and C are real numbers. I mean, that's the only restriction. A traceless matrix has to have, traceless 2 by 2 matrix has to have the sum of the diagonals be 0, which forces them to be negatives of each other, like so. And, yep.
Sum of only the forward diagonal.
Right. Mm-hmm. Yeah, trace is sum of diagonals, so. And, oh, you want me to do more?
No,
okay,
no,
okay, fine. And A transpose equals to A. So we'll add the symmetric condition. There we go. But I was just content with my example, so we'll add symmetric to this W, make it more fun. There we go. It's the kernel of the trace intersected with the kernel of the antisymmetrizer. You're like, what's the antisymmetrizer? Well, I'm so glad you asked. The antisymmetrizer, antisymmetrizer of a matrix M would just be M plus M transpose over 2. And the 2 is optional. I just feel like you should go there. You don't have to put it there if you don't want to. But anyway, the point is that minus, there we go. And so if you look at that, the kernel of that forces that M is symmetric which gives me my W. Hey, why'd you make me drop my marker? Monster. Yeah, what?
Why is the 2 optional? Just because.
I mean, you set this equal to 0, you divide by 20 and set it equal to 0. Still, we have the condition that M is equal to M transpose is the kernel of the anti-symmetrizer.
So you don't need it to be a fraction at all.
Not really, no.
If you're looking at the kernel, but like in general, that's the definition, right? Is that what you're saying?
Oh, I wouldn't say there's a general definition of anti-symmetrizer. Actually, the ambiguity I'm talking about is exactly the ambiguity that we'll find from book to book. I'm actually not joking at the moment. There is something called an anti-symmetrizer and a symmetrizer, and whether or not you divide by 2, it's a question of the combinatorics you're interested in. So.
Okay, I'm not trying to be picky, but in beta V over W, J is equal to K plus 1. Should that just be N rather than Vn?
Oh yeah. Please do be picky about that. That is definitely a rather unfortunate typo. Thank you. I'm happy that I've only made that one. You guys realize that we don't have to talk about kernel at all here. We could just write the thing in curly brackets and be done with it, right? Okay. Anyway, the point is that this is W, right? So this is the span of 1, 0, 0, minus 1, 0, 1, 1, 0. Yeah. And you can see that this is going to be a basis for W, yeah? All right. Let's try to let's go back to Bethany's original request, which was to actually focus on the coset aspect of things and talk about how to calculate in cosets. Let's do that. So what is V mod W? In other words, I'm actually not going to use the theorem. All right, so V mod W is allegedly A plus W, right? Such that what? Such that A is an element of R2 by 2. Right? That's the definition of the factor group here, which is also the quotient vector space. Now, what is W? Well, we know what W is, but we don't know. Let's be more explicit about A. Let's say A is A, B, C, D. Right? And so explicit and direct calculation requires, I guess I don't need that anymore. I could say, Soprano's a bad influence. Let's hear CD in the reals. You see, I need to have some sort of some spark of inspiration to see how to write that. Oh man, I don't know if I can do it. Oh man, it's really tough in my current example. Maybe I have to use the theorem. I'm trying to think of how do I make my matrix appear as something that looks like this and something else. Because I basically need a creative way to add. I don't know. Goodness. Well, I mean, fine. I have managed to make an actually kind of difficult example. Your homework problem's easier. Because your homework problem lives and dies on the this identity. Which is ever so much nicer. So I'm stuck on, see, doing that. See, this is symmetric, yeah? And this is anti-symmetric. So if I can take a matrix and rewrite it like that, if I'm working with W, okay, so like just sidebar, I'll get back to my stated problem in a second. It requires more mental energy than my current comment. So if we were working with, let's say, watch it doing to me. If we're working with A plus, I need names. So W1 equals the symmetric Rn by n by n matrices. And if we're working with W2 is the anti-symmetric n by n matrices. You'll notice that I am no longer able to use S sub n and A sub n as labels for these. We've used those for other things in this course, have we not? And anyway, my point to you is that A plus W1 is actually equal to 1/2 A minus A transpose plus W1. I think this is actually answering your question, Bethany. Because this is the point, is like I can absorb the part of A which is in W. That's the idea, basically. So you have to identify the part of the representative which is inside the coset. Whatever that is, we can absorb that into the coset. That's the calculational feature that's new. And likewise, if I take A plus W2, because W2 is antisymmetric, it eats the antisymmetric piece, and it leaves that. So what this calculation shows, if you really think through it, is there's as many W1 cosets as there are, in some sense, distinct W2 elements. And there are as many W2 cosets as there are distinct W1 elements. And if we're just talking about how many, that's not particularly interesting because all of these have the cardinality of the continuum, so big deal. But if you think about dimension, it's more interesting because, you know, the dimension of the factor group, the dimension of the quotient space by symmetric matrices is the dimension of the antisymmetric matrices and vice versa, is what that theorem actually says. The trouble I'm having here is it's hard for me to break this into two pieces that are analogous to these two pieces and see what to absorb in that W, because that W I have foolishly created to be more complicated than I should try at this point in the day. I have no choice but to extend my basis to a basis for our 2 by 2 to make progress here, unfortunately. So like, how would you extend beta W? To, what would you union it with to get a basis for everything? I'll tell you what I want to do. I want to use the identity matrix because that is clearly linearly independent from this guy and that guy. And then I want to use that because that's actually linearly independent from the other one and also that one. And so look at all four of these together. Pretty sure they're linearly independent. Which means that, which says to me then that V mod W I can build as the span of 1, 0, 0, 1, 0, minus 1, 1, 0, because again, that's the part of the basis for our 2 by 2 which is not in W. Now, but to really understand how to, I would need to understand how do I find A, B, C, D equals to C1. I need C1 times, well, I mean, how am I going to order this basis? I guess I'll do the beta W first. 1, 0, 0 minus 1, plus C2, 0, 1, 1, 0, plus C3 times my identity matrix, plus C4 times my 0, 0 minus 1, 1, 0. And C, to really find the formula I need to figure out what C1, C2, C3, and C4 are in terms of ABCD, which you could do we got that. We got what? We got C1 plus C3 equals to A. We've got C2 minus C4 equals to B. We've got C2 plus C4 equals to... This is an awesome problem for linear next semester, am I right? So, minus C1 plus C3 equals to D. Man, this is nasty, but it's not so nasty that it's not a good homework problem, right? It's 4 equations, 4 unknowns, but look at them. They're cuddly, right? Or are they? Well, I guess we can add the middle two. That gives us that 2C2 is equal to B plus C. So C2 apparently is B plus C over 2. Oh, we can subtract them. And also we get C4 is equal to C minus B over 2. And these two, adding them, we get A plus D over 2 is equal to C3. And apparently A minus D over 2 is equal to C1. So this is what I, for some reason, couldn't think off the top of my head, but in fact, you can rewrite this as what? A minus D over 2 times 1, 0, 0, minus 1 plus B plus C over 2 times 0, 1, 1, 0 plus A plus D over 2 times the identity plus C minus B over 2 times 0, minus 1, 1, 0 plus W. And A, B, C, D are real numbers. And then, now that I have done the... See, your homework problem is much nicer than this because it is built over the idea that you know this from linear. But that's inaccurate, right? Because you don't know it. Hey, otherwise, why would you? Well, anyway. So then you guys tell me, what does this simplify to? Which of these gets swallowed up in a W? The traceless symmetric pieces, right? So this piece and that piece, these ones, they just get eaten into, they're W things, so they get swallowed into W. That's the way the coset calculation works. And then we have A plus D over 2, 1, 0, 0, 1, plus C minus B over 2, 0, minus 1, 1, 0, such that A plus D and C minus B are real numbers, right? Well, we could add a 2 while we're at it. And you could see that, oh, and I've lost my plus W. Sorry about that. And so generally speaking, we've got, C3, 1, 0, 0, 1, plus C4, 0, minus 1, 1, 0, plus W, such that C1 and C3 and C4 are real numbers, which illustrates the fact that the basis for the quotient vector space here is given by the identity plus W and 0, minus 1, 1, 0 plus W. These are linearly independent in the quotient vector space. We can prove that. So it has dimension 2. So guys, can you tell me why, I asked the question in that homework problem you're asking me about. Why is this not contradict Lagrange's theorem? What's that? I mean, let me put it all out here so we can, because I'm sorry, I should write something down to have this discussion better, right? Lagrange's theorem said what? It said that the index of a subgroup is the order of the group divided by the order of H, right? We've just observed that the dimension of V over W, right, is equal to the dimension of V minus the dimension of W, actually. And so what I'm trying to confuse you about, well, I'm trying to tempt you to engage in your usual confusion. The usual confusion is to think that dimension is the number, is the order. So the number of cosets would be this. What's the number of cosets in this example? 2. But no. See, because the number of cosets, notice that C3 and C4 are real numbers here. The number of cosets is infinity. It's the continuum, right? So this is equal to infinity. But you know what? The order of V is equal to infinity. You know what? The order of W is equal to infinity. These are all infinite groups. Because vector spaces have infinitely many points over the reals. So does Lagrange's theorem apply? No. Lagrange's theorem is for finite groups. So it is not even partly troubling that we don't have the same result. It's just that dimension is the closest thing we have to counting for vector spaces. But dimension captures a finiteness in terms of basis, like the basis for the vector space. It gives us a way of counting how big it is in that sense. But in the more gross sense of just counting points, they all have the same size. The cardinality of any vector space over the reals is just the continuum. Vector spaces of different dimension have the same cardinality.
So it doesn't contradict the theorem.
Theorem does not apply, right? But these are analogous results, right? It's just that the division has been replaced with subtraction, and the dimension of the quotient is playing the role of the index to the subgroup. I mean, there is something a little bit more nuanced to say than just that it doesn't apply, but doesn't apply, we'll get you full credit. I'm just saying there's more to appreciate here than just that.
So I have a question, because that index part is equal to the order of G mod H, right?
That is true, yes. For a finite group, of course.
So will you never have like an order of G that doesn't divide your order of H?
Well, in the infinite case, I just don't know what to say. Because the order of G is infinity, the order of the order of V is infinity, the order of W is infinity, the order of the quotient's infinity. Infinity over infinity is still infinity. I mean,
What about for finite groups, though?
for finite groups, Lagrange's theorem is general. So the argument we used for Lagrange's theorem was just to take a subgroup and to partition the group into cosets and to count. That didn't involve cyclic, it didn't involve anything. I mean, it didn't involve abelian even, just the finiteness was all that was required. And the arguments we made for distinctness of cosets and the fact that they partition, those are totally general arguments. We could even use right instead of left cosets, it wouldn't change anything. Does that help? I'm not sure, it's maybe not things, you're still looking for an example with cosets that's not this, right?
I guess my question is, if you're trying to form that factor group,
Yeah.
you take, like, so you have your group G,
Mm-hmm.
and then the subgroup H. So to form the factor group, are you just looking for things that aren't already in H? And
Yes.
then adding H to that thing?
Right, so here's the logical process. You've got like H. This is the group G, right? So as you're forming G mod H, suppose we're in the multiplicative context. Logically, here's how I start. I go H. H is a coset. Yay, we're done with that part, right? So what's the logical step? So you can forget about everything inside H. Your next move, you pick a point, A1, that's outside H, right? A1 not in H. And then, guilt by association, A1H is going to be something like that, right? And it's as big as H if we're talking about a finite group, yeah? This process of picking the next one did not work for the quotient vector space construction, right? Because it's a problem of linear algebra, which requires continuous techniques. This Mickey Mouse number theory garbage isn't going to help us there. I'm sorry, we love number theory. Number theory is important and interesting. I mean, I do think the number theory Dr. Smith does is very interesting, actually. But anyway, so the next thing to do is to pick an A2, right? And that will give you A2H, right? And the deal is A2 is not an element of H union A1H, right? And then you just keep doing this, right? Until you exhaust. And you know how many you're looking for by Lagrange's theorem, right? Lagrange's theorem says that the order of G over H is equal to the order of G over the order of H, right? So that's my K here. Although, oops, K minus 1, given my numbering, which was poorly chosen because I started at 0. So to get K, I go to K minus 1.
So then if you intersect H and A1H.
So you guys, yeah, I'm sorry. Any two of these should intersect the empty set. You guys have questioned. The intersection is the empty set between cosets and H. So, and the other thing to watch out for, you guys, is just, you got to keep in mind that there's not a unique representative, right? So if you were looking at something like, I don't know, D5, right? Sorry I'm going late. It's you guys' fault. You talk after abstract, and that bumps the complex, and then it bumps this, and then before you know it, I'm going to be in trouble. The order of A is equal to 5, the order of B is equal to 2, and we've got, I just like to say it, Baba, equals to 1 is one way we could say it. I mean, whatever. However you want to capture that identity. But if we are to look at, for example, the subgroup K, let's say generated by B, it's got 1 in B, right? For some reason, I'm using 1 instead of E all of a sudden. My apologies. And so how many cosets? You should have in mind what your target is before you start calculating. How many cosets? 5, right? Because 10 divided by 2 is 5. 5 cosets. So that's 1. And then if we look at AK, right, that's going to give me AB. And I like to write that as a B8 at the fourth in this context. I think that's right. The inverse of A is 8 to the fourth, right? Yeah. So this is also equal to so my point here was that this was also equal to B8 to the fourth times K. Now you got to pick something that's not already, and the reason I'm rewriting it that way is so that we have it in the standard presentation, which for us has been A to the power and then B times A to the power. So next up, A squared K, right? And that gives me A squared B, which is A squared BA cubed, I believe. So this is also BA cubed K. I mean, I see a pattern here. You know what I'm going to do for the next one? I'm going to do A cubed, right? because I don't have a cubed, right? So you can see that a cubed k and a to the fourth k, those are going to be distinct from what I already have, right? Because the first component gets you the a to the power, and the only way you can get that is to multiply e by that. You can't ever get it from the second thing. Anyway. On the other hand, if I was to let h equal to the cyclic subgroup generated by A, how many cosets? Two, right? 10 divided by 5 is 2. And this is much easier. What's the only other coset? You got to pick something that's not in there. You can't go wrong. Got 5 choices. What? B. B is the correct choice. So BH is B, BA, BA squared, BA cubed, BA to the fourth. And by the way, this is equal to BA H. This is equal to BA squared H. This is equal to BA cubed H. This is equal to BA to the fourth H. There is a 5-fold degeneracy in the representative for a coset of order 5. These are the calculations you're looking for, I think. See, Emily, I brought the book. I was ready for today. But do you have questions from here? You should always ask them. Maybe next week we spend most of the time on your questions. How about that?
Okay.
All right. So next week is answering questions from the book week.
Actually, next week we don't have fall break.
Oh.
I mean, you're more than welcome to do it next week.
We do have fall break. That's right. I will not be here. Oh, thank you. Now I have to go home and write a solution to this. I am too tired for that. Just move your test. You guys are funny.
Move the test, do it tomorrow.
Yeah.
Yeah, move the test to Wednesday. Teach what you were going to teach on Wednesday on Monday.
Uh-huh.